Welcome to Numerical Analysis. Today we are going to explore algebraic and transcendental equations. Imagine you are tracking a submarine moving through the ocean. At 1 p.m., it is 50 meters below the surface, and at 2 p.m., it is 50 meters above. Even if you closed your eyes, you know with absolute certainty that at some exact moment it broke through the surface of the water. Finding that exact time and place is what we call finding the root of an equation, and that is exactly what we will learn to do today. Now that we have our submarine analogy, let us formalize what this means mathematically. Why does finding a root matter? In the real world, relationships are rarely simple. Engineers need to find exact points where forces balance out to zero or where a trajectory hits the ground. The surface of the water in our analogy is the horizontal axis. The path the submarine takes is our function. The root is simply the exact value of our variable that makes the entire equation equal to zero. Sometimes we have a simple formula, but often we are flying blind and must use numerical methods to systematically trap this value. This brings us to the standard mathematical representation of the problem we are trying to solve. Conceptually, this formula is the starting point for all root-finding methods. The symbol f of x represents our function, which could be any curve. The variable x is the unknown value we are searching for. Setting the function equal to 0 represents our ultimate goal, finding the exact point where the graph crosses the horizontal axis. As x increases or decreases, the value of the function moves up and down. Our job is to find the specific x that makes the function exactly 0. Before we can solve these equations, we must understand the two main types we will encounter, starting with algebraic equations. Why do we classify them? Because knowing the type of equation tells us how difficult it might be to solve. An algebraic equation is a mathematical statement built entirely out of polynomials. This means it only uses basic operations like addition, subtraction, and multiplication. Furthermore, the variables are only raised to positive whole numbers, like squaring or cubing a number. If your equation only has basic math and whole number powers, it is strictly algebraic. Let us look at a concrete example of an algebraic equation. This formula is the classic quadratic equation. It comes from basic polynomial math. The symbols a, b, and c represent constant numbers, while x is our unknown variable. Notice that the variable x is only being squared and multiplied by numbers. Because it only uses these basic whole number power operations, it fits perfectly into our definition. If we increase or decrease the constants a, b, or c, the shape of the parabolic curve changes, which physically moves the location where it crosses the zero line. Now that we understand algebraic equations, let us look at the other category, transcendental equations. These are incredibly important because many natural phenomena like radioactive decay or oscillating waves cannot be described by simple polynomials. A transcendental equation is one that transcends or goes beyond basic algebraic operations. It contains special, more complex functions like trigonometry, logarithms, or exponential growth functions. Because these functions behave in complex, nonlinear ways, these equations are notoriously difficult to solve exactly using standard algebra. This is exactly why we need numerical methods to approximate their roots. To see what makes them so complex, let us examine this formula. This is a clear example of a transcendental equation. Conceptually, it combines two very different types of mathematical behaviors. The symbol e to the power of x represents an exponential function, and sine of x represents a trigonometric wave. As the variable x increases, the exponential part grows very rapidly, while the sine part simply waves up and down. This makes their combined behavior highly complex. Because it goes beyond simple addition and whole number powers, it transcends basic algebra, requiring numerical approximation. So, how do we actually find roots for either type of equation? We rely heavily on a concept called the intermediate value theorem. This theorem is the beating heart of numerical root finding. It states that if a continuous function outputs a negative value at one point and a positive value at another point, it must cross zero somewhere in between. A continuous function simply means a smooth curve that you can draw without lifting your pen. If you walk from a valley below sea level to a mountain peak, you absolutely must cross sea level along the way. This brings us to the mathematical way of writing the intermediate value theorem's trapping rule. Conceptually, this formula is a simple test for opposite signs. The symbol f of a is the height of the function at our starting point, and f of b is the height at our ending point. By multiplying them together, we are checking their signs. If one is positive and the other is negative, their product will be less than 0. When this condition is true, it guarantees that at least one root exists between those points. If both were positive, the product would be greater than 0, meaning we have not trapped the root. Let us look at exactly what this theorem means visually. In this diagram, you are seeing a smooth blue curve representing our continuous function. The horizontal axis is our zero line. Notice our starting point on the left, labeled a. The function's value here, f of a, is clearly negative, sitting below the axis. Now look at the ending point on the right, labeled b. Its value, f of b, is positive. Because the curve is continuous, it has no choice but to slice through the horizontal axis to get from a to b. That red dot where the crossing happens is the root we are hunting for. Now that we have our visual intuition, let us put this theory into practice with a basic problem. We are given the algebraic equation x cubed minus x minus 1 equals 0. Our task is to prove that a root exists somewhere between x equals 1 and x equals 2. We choose this approach because the intermediate value theorem is perfect for verifying roots within an interval. Our first step is to define our function f of x by taking the left side of the equation. This gives us a clear expression where we can substitute our boundary values. Continuing with our strategy, we begin by testing the lower boundary of our interval, which is x equals 1. We replace every instance of x in our function with the number 1. This step is done to find the height of the function at the very start of our search area. After performing the basic arithmetic, we find that f of 1 equals negative 1. The most important takeaway here is not the number itself, but the fact that it is a negative value. This tells us that at x equals 1, our function is underwater, below the zero line. Finally, we test the upper boundary of our interval, which is x equals 2. Just like before, we substitute 2 into the function to see where it is located at the end of our interval. After calculating, we find that f of 2 equals 5. The crucial detail is that this is a positive value. Because the function went from a negative value of negative 1 to a positive value of 5, the intermediate value theorem guarantees that it must have crossed 0. Physically, this means our submarine has breached the surface, and a root definitely exists between 1 and 2. Let us try a slightly more complex problem involving a transcendental equation. We are given the equation x times e to the power of x minus 1 equals 0. We need to determine if a root exists between x equals 0 and x equals 1. This is transcendental because it contains the exponential function e to the power of x. Our approach remains exactly the same as the previous example because numerical methods do not care how complicated the equation looks. We start by defining our function f of x from the left side of the given equation. We test the lower boundary by substituting x equals 0 into the function. We do this to establish our starting position. Remember from basic math rules that any non-zero number raised to the power of 0 is exactly 1. So e to the power of 0 becomes 1. Multiplying 0 by 1 gives us 0 and subtracting 1 leaves us with negative 1. Just like in our first example, the function starts at a negative value. The curve is currently below the horizontal axis, waiting to see if it will rise. Now we test the upper boundary by substituting x equals 1 into the function. Any number raised to the power of 1 is just itself, so e to the power of 1 is simply e. We use the approximate value of e, which is 2.718, to see if the result is positive or negative. The calculation gives us approximately 1.718, a positive number. Because f of 0 was negative and f of 1 is positive, the sign has changed. This physically proves that our complex transcendental curve crosses the zero line. We have covered a lot of ground today. To summarize, algebraic equations are built from basic math and whole number powers, while transcendental equations involve complex functions like exponentials and trigonometry. Regardless of the type, our goal is always to find the root, which is the exact value that makes the equation equal to 0. By testing different points and looking for a change from negative to positive, we can trap the root using the intermediate value theorem. You now have the foundational tools to start solving complex real-world engineering problems. Great job today!